Now today starting about the circular motion and rotational motion related to in brief and talk the summary about all the videos regarding all the videos previously done. Now we here consider first of all this thing. We started about firstly circular motion, right? Circular motion. It's about the body, circular motion. Initial point in P1, P, then after theta displacement, theta angular displacement, it will come to Q position. Here, this is considered about the uniform condition. All are the uniform condition. Uniform velocity, uniform velocity, and uniform angular velocity condition. Here, tangentially acting about the velocity. Here, velocity, same velocity. We will not change. There's no angular acceleration also. And omega is the here initial omega. Here is also in finally omega here. Omega not change. Radius of R. This formula we derived all these formulas. V equal omega. V equal omega. From that, omega is the angular velocity, radius R, the linear velocity. And another thing we take, V equal omega R, theta equal omega T. Theta equal omega T. Angular displacement equation. And periodic time T equal 2 pi over omega. 2 pi over omega. And frequency F equal 1 over T. You can calculate here 5 over 2 pi. 5 over 2 pi. This is for the uniform condition for the formula. Then we came to earlier ununiform condition. Ununiform condition. Ununiform condition, what is happening? Omega changing, V changing, all those things changing. Displacement only changing with the time only. Others also all are changing. Now that this is discussing about thing here, ununiform condition, it means this is the angular circular motion, is initial point P. We also have omega naught. Omega naught. After it will come to time T, omega angular velocity. This velocity is also V1. Here again V2. This displacement like this theta. Right. What are the formulas we take? We know that angular velocity changing, it creates the acceleration, angular acceleration. Time is t, p to q, time is t. dpt equals 0, here t equals t, right? T equals t. Now, angular acceleration alpha is equal omega minus omega naught over t. From this equation, you will get in omega equal omega naught plus alpha t. This is the change in velocity and angular acceleration relationships. In the relationship of theta, theta is equal omega naught t plus half alpha t square. This is also my video already expressing all the things. Yes, this was expressing. Another one, omega squared equal at that. Omega naught squared plus 2 alpha theta. In this condition, angular acceleration acting where? Actually, the angular acceleration of the acting force tangential to the circle. R alpha. Angular acceleration R alpha. And centrifugal acceleration another component like this here. Omega squared R. There are two components here have what are two components each other perpendicular. One is R alpha tangentially, and the one is omega squared R. Right? Sometimes problems say actual acceleration, what is the actual acceleration? Actual acceleration, these two accelerations resultant. Resultant should be we have to obtain. Right? Resultant you have to obtain. These are the condition for unhome condition. Right? Those are the things. And this is called normally centrifugal acceleration. Centrifugal acceleration. Right? Centrifugal acceleration. All those things. Right. Now we consider the motion about the rotational motion. What is the rotational motion? Rotational motion, we have to consider first moment of inertia. Moment of inertia. What is the moment of inertia? Moment of inertia is the mass into distance square. Distance square. Distance square. We say somebody like this. This axis, this rotate. Rotate omega angular velocity. If we say small mass here, M, the body contains so many masses, right? Small particles we say delta F. The distance close to there R. Then moment of inertia I delta small mass equal delta M R square. Delta M R square. Now all the masses if we are taking I is equal MR square. MR square. Given masses, right? I is directed this direction. I. Okay. So the moment of inertia mass into all the time distance square. Distance to the mass square. Now we come into the geometrical shape bodies, moment of inertia. First we take the uniform rod, length L uniform rod, right? Length L uniform rod. Perpendicular action go to the center of gravity here. Perpendicular to this rod. This L is the length. The mass of the sun M. Right? Then A axis, A dash axis, moment of inertia I, A dash equal 1 P times ml square. Right? And the condition we are taking moment of inertia in the uniform rod in the one cone, right? One N going to the axis, perpendicular to the this rod, this axis, omega. Mass M same. This moment of inertia given normally I equal 1 over 12 ml square. 1 over 12 ml square. Right? This is the moment of inertia of this. Sorry, this is the 1 over 12. This is 1 over 3. Sorry, extremely sorry. This is 1 over 3. 1 and 1 over 3. This is 1 over 12. Right. Now we come into disk. Uniform thickness disk. Uniform thickness disk. Right? Uniform thickness disk. Moment of inertia. Solid disk. Number 2, solid disk. Now we are taking solid disk. What is the moment of inertia? Then, like this, more this. This rotate this axis, right? Omega, this axis. This mass M, this radius is R, right? Moment of inertia at this axis, I equal perpendicular axis, huh? This plane to perpendicular this thing, perpendicular this thing, equal half M A square, radius A, radius A. Now here you consider the same time I am doing the solid cylinder. Solid cylinder actually longitudinally this axis. Axis alongside. Thin alongside. Along. Axis along. This extend anyway. This is not independent with the height. Independent with the height. No difference, no change. Like this cylinder. Like this cylinder. This axis. This is A. M. In moment of inertia, I equal, this is also half ma square. Only mass only change. Half ma square. Right? Half ma square. Right. This is the directly you can deduce that from to here. This is half ma square. This is also half ma square. In longitudinally, and then vertically, height not take to the moment of inertia. Any height also same one. Right. But change in the radius, that is changing. Now we come into the moment of inertia of the circular ring. Circular ring. Circular ring, actually, practically, you are taking the radius. Average radius, only some questions you are getting average radius. Circular ring here. We say average radius A. Average is A, M. This is also I equal, this will come ma square. Ma square. I equal ma square. Right? I equal ma square. Now we come into the hollow cylinder. Hollow cylinder. Hollow cylinder. Hollow cylinder also same one. It is not depending on the height. Like this. Right? Here I equal ma square. This is a division. That you like the revision, listen, to all those things, memorize you. Right. Now, another coming, solid sphere. Solid sphere. Solid sphere. You remember solid sphere, 205 ma square. How to come? This solid sphere. Sphere, solid one. Right? Solid one. Then center through axis. This rotate. Center through axis. Mass is M. Radius is A. The moment of inertia in this axis, 205 ma square. Ma square. Right. 205 ma square. Now hollow sphere, hollow sphere, hollow sphere participant like this, hollow sphere, it's hollow, inside no nothing, right? Moment of inertia I in through this axis, this is going to the center, 2 over 3, 2 over 3 ma square, 2 over 3 ma square, right? This is the moment of inertia, you have to remember all those things, right? Moment of inertia, you have to remember all things. Yes. Now we come into the new thing. Rotating body. What is the rotating body? What are the rotating bodies? Rotating bodies. There's a rotating on axis. Actually includes the moment of inertia, that type of axis. No, there's the moment of inertia all the time having rotating body in on axis. Rotating body. This is the rotating body. We say we example we take a disc like this, right? Omega. Moment of inertia I for this axis I, right? Then it will rotate. We say acceleration, angular acceleration alpha, angular acceleration alpha. Due to the rotation, it will given we say torque given to the here, torque given to the here. What is the relationship here? Cal alpha have I have is the relationship I have the tau equal I alpha, tau equal I alpha. You remember this tau equal I alpha, right? Tau equal I alpha. And the rotationally, we say rotationally the work done due to the rotation. We say this turning about theta angle. Theta angle we torque tau, theta angle by tau. Then work done. Due to work done, this rotate some theta angle, work done is equal. What that? Can we say work done? Well, normal work done, what is the linear condition is work done? Force into displacement. Force into displacement. Here, torque into angular displacement. Torque into angular displacement. Torque into angular displacement. Come here, have the rotational power. Rotational power. PR. Rotational power. What is the rotational power? How can get? Easily you can get W over T equal time for theta over T. Theta over T. Right? Theta over T. W over T rotational power. PR. Rotational power equal theta over T is omega. Omega. Tau omega. Tau omega. Torque into omega. Right? Rotational power torque into omega. This is uh, this all the previous video I discussed. If you want to see again and again, you can learn more about these things. Right. Now we are here. Is the rolling body. Total energy of the rolling body. Now we come in the total energy of the rolling body. What is the total energy of the rolling body? And the rolling body in the we say smooth plane rolling like this. Radius A, radius A, radius A, right? It will come to A. That linear velocity actually acting through here V, this part V, linear velocity V, right? Due to the linear velocity, total energy we are taking is equal kinetic energy is m mass m half m a m v square half m v square. Due to the rolling, in angular velocity also have omega. Here omega also same like this, omega same, not changing, right? Omega to the angular kinetic energy. Angular kinetic energy half I omega square. If the total energy is due to the rolling energy plus linear energy. Degrees of the addition, Et equal I me square I or omega square. This is the rolling body. We are taking from rolling body like this. Now we come into the again I express in the conservation of angular momentum. What is the conservation of angular momentum? If there is no external torque, if there is the rotational body, external torque, if they are not the rotation during, there's torque, there's no torque, nothing torque, right? There's no torque. All the time, angular momentum is conserved. Angular momentum is conserved. Constant. Actually, angular momentum constant. L equal I omega. Angular momentum L equal I omega. Is rotationally one that rotation is usually omega here, I here, then angular momentum L equal I omega. Right? If the change in the if you want to change in the angular momentum, what to do? You have to apply the torque or any external thing. Right? You have to apply the torque or any external thing. This is a short video about the previous all those things discussing. Right? Thank you very much for watching. Now learn and learn more. See my videos series, rotational motion and circular motion video. Right.